Hi there, everybody. In this section, we are going to start Chapter 2. So I'm just going to start with a real quick overview of Chapter 2 here. Nothing fancy to start off. So Chapter 2 is where we learn what happens after data are collected from the cases. And so in this chapter generally, so it's a very long chapter, it's 7 sections, we learn about how to display and summarize data, and graphs display information, and summary statistics summarize, so they quantify aspects of the information. So we're just going to be looking at ways to learn something about the cases that you took the data from. And the graph or statistic we use depends on combinations of variables. So again, just a little 2-slide overview here. This is what we're going to be doing. So this video will be section 2.1 only. So we're going to look at what happens when we have one categorical variable or 2 categorical variables in a study. And we're going to see examples of what can go on. As you can see, the other sections coming up, 2.2 through 2.6, all are very rigidly identified with certain combinations of variables. And then section 2.7 is just everything else, just a mix of variables that go above and beyond combinations of 1 or 2 variables. So let's jump in to section 2.1. As you can see, we're going to be using calculators today, so make sure you have yours handy. I'm not going to do a ton of calculations. I'm just going to go over a couple of the basic calculations as we work through the problems, and then I'll just kind of expect that you can do it from there. None of the calculations today are very crazy or difficult. All right, so here's your section learning goals. You guys know how to read that stuff. That's the videos that are available in the ebook at the end of the section correspond to these learning goals. We're going to talk about all this stuff today. So let's start what happens when we have one categorical variable. So when there's only one categorical variable, we use a frequency table, and you can see the frequency table down there at the bottom. So this example that we're going to be using initially here is a 2009 study that looked at 119 participants playing rock, paper, scissors. That might sound silly, but believe it or not, there's actually a tournament, a rock, paper, scissors tournament, statewide, and then if you win that, you go nationwide. There are strategies to win at rock, paper, scissors, it's true. And you can see what everybody chose. So 119 people paired off at rock, paper, scissors, and everybody went, 1, 2, 3, go, and this is what they chose. So you can see 66 people picked rock, 39 paper, 14 scissors. So what we want to do is compute the proportion of people in each category. So again, it's called a proportion or a relative frequency. And the way you compute a proportion is you take the number of data values in a category and you divide by the total number of data values. So just from talking to students for the first couple days, I can see that some students are already mixing up the idea of a variable and a count in a category. So when we talk about number of data values in a category, that is your count, right? So if you look back at the table, the variable here is which option was selected, rock, paper, or scissors. The frequency, so the count, is how many people picked each option. So the variable is not rock, right? Like paper is not a variable, scissors is not a variable. It is the chosen value of the variable, and then the count or the frequency is how many people picked each one. So just make sure you understand that a variable is something that has to be different for different people. For categorical variables, it has to be true. For quantitative variables, you could mix up the idea of variable and value of the variable, but for categorical variables, you really can't do it, right? Rock is not a variable. It is a value, or a chosen value in this case, and it has a frequency or a count. So the proportion is the number of data values in each category divided by the total number of data values. So you can see what's going to happen when we start computing stuff here. The total number of data values is going to be the same. right? And if you go back one slide, you'll see it, right? 119 people total. But there are 3 categories. So there's going to be 3 proportions. And the number of data values in a category, so that numerator has to be a positive number or 0, and it must be less than or equal to the total number of data values, right? And that should be clear. Again, going back to the example, the number of people who selected rock can't be bigger than the total number of people in the tournament. It just doesn't make sense. And it can't be less than 0. Maybe 0 people picked rock, but that's the smallest it could possibly be. So that's where this comes from. So let's jump in, do an example, and see how this works. So find the proportion of players who chose each category, round to 2 decimal places. Find the percentage of players who chose each category, round to 2 decimal places. So I'm going to go ahead and do A and B just for the folks who selected rock. When we get to the answer key, pause it, pause the video, and you try to do paper and scissors on your own, and you can check my answers, or check your answers against mine. All right, so what we're going to do, I'm going to go over here and turn on the calculator. So the proportion of players who chose each category. So just go back and look at what we're doing. We're looking for a proportion, number of data values divided by the total number. So if we're looking for rock, 66 people chose rock. So I'm going to make a fraction, right? 66 people chose rock. And there were 119 total. And you hit enter, right? So if you type it in as a fraction, it gives it to you as a fraction. You may have to, depending on your calculator, how it's set up, you may have to type it in as a division problem. Okay? So just double check on your calculator. It depends on the mode. I talked about how to set up the mode in the technology video. But if you want it to always come out as a fraction, you can do that. If you want it to always come out as a decimal, you can do that. And if you type it in as a fraction, your answer will be a fraction. If you type it in as a division problem, your answer will be a decimal. So just use the option that fits how you have your calculator set up. All right, so we want to round this to 2 decimal places. So we can see here that we have 0.5546218. 2 decimal places, that's this 5. So we want to round, so it's either going to be 0.55 or 0.56. This 4, so there's our rounding digit. You look to the right, that 4 is less than 5, so we do not round. I'm sorry, we do not round up, we round, right? So again, make sure that everybody is getting this, and if you're not, pause the video, keep typing it until you get it. Let's go back and do rock for part B. Now it says to find the percentage of players who chose each category. So when you do a percent, you can't just take your answer from part A and call it 55%. You're not allowed to do that, because that 55% doesn't have any decimals. So what you have to do is you have to multiply your answer here by 100, so just times 100. Now we round this to 2 decimal places. So the 6, so this is our percent. The 6 is the rounding digit, 2 is less than 5. So when we round it, it's just 55.46, right here. All right, so I'm going to put the answers up. Go ahead and try, pause the video, type the numbers in for the other ones, and make sure you can round them. For paper and scissors, and then I'm going to keep moving on. If you feel comfortable doing this, then you're good to go. But there's your answers. If this is a homework question, this is what they want. If this is a test question, this is what I want. I want you to show the work, or at least show the steps. You don't have to write in like all the little details, but you have to show me the steps you're using. All right, moving on. So a proportion allows us to compare results from samples and populations of different sizes. This is why we use them. right? So if we want to compare one rock, paper, scissors tournament to another one, they're going to be different sized in terms of the number of people participating. But we can see that 55.46% of the people in this tournament chose rock. We can compare that to a different tournament if we scale everything. So you divide by the total number, multiply by 100, and you get a percentage. So a proportion is a number between 0 and 1 inclusive, right? And we can see that from this example here. 66 divided by 119. This number has to be a number between 0 and 119. So this is going to be a number between 0 and 1. This is going to be true for the entire course. We are going to look at numbers between 0 and 1 450 times. I'm just making that number up, but a whole bunch of times this semester. If you see the word proportion, it has to be a number between 0 and 1. Okay? Proportions can't be negative. They can't be 1.2. So just be real aware of that. And then obviously we turn proportions into percentages by multiplying by 100%. I just did that for this first example. And the last bullet, pay close attention to rounding rules when percentages are calculated. Always round as your last step. You never want to round and then do further calculations. Okay, so if you need to keep 2 decimal places and you start rounding and then doing other stuff, your answer won't be accurate to 2 decimal places. It's very important. A lot of this class depends on, are you following the rounding rules to the correct number of decimal places? So there's going to be a lot of points on all of the exams that really depend on, are you following the directions? So just pay very close attention to that. All right, moving on. So a pie chart is one way that we visualize categorical variables. So here we're not looking at rock, paper, scissors. I'm switching the example up. This chart shows the percentage of concussions caused by different sports for all children ages 5 to 18 who were admitted to an emergency room in the US in the year 2012. A lot going on there, right? But you can see what's happening, right? You can see that bicycles accounted for 23.2% of all concussions among children who were admitted to an emergency room in the US in 2012. Football was 20.1%. Obviously, we pick on football a lot because it definitely has a lot of concussions associated to it. That's why they wear helmets, right? And you can see other sports as well. Basketball accounted for 11.4% of concussions, playground accidents 10.3%, and so on and so forth. So if you want to, I'm just going to go through this stuff really fast. If you ever want to take more time and look at anything, just pause the video, or and then if you want to take notes, like if I'm speaking too fast, you can just pause the video and write your notes out and then start the video up again. So here's the same data set. It's just in a bar chart form. So a bar chart is just vertical bars, and it represents the frequency or relative frequency. So it turns out that here, this is the frequency, right? This is the count. So you can see that around, around 23,000 kids had concussions because of a bicycle accident. If you go back and look at the pie chart, I had scaled everything on the pie chart into percentages. So you can set this stuff up to do lots of different things. So I'm just showing you all the different options. It doesn't matter if you list the percentage or the frequency in general. You just pick what works for you for for whatever you're trying to display. So if you're doing a presentation and you want it to appear a certain way, pick percentages or pick the frequency. It doesn't make any difference. One other thing I do want to say about this bar chart and the pie chart. Let's do the pie chart because it looks a little nicer. So questions come up all the time about explanatory and response variables, and you have to be really, really, really careful when you're doing the homework. So think about what the response variable is here, okay? So think about who the cases are, and is this a sample or a population? So you have a homework problem that looks like this, so that's why I'm going over this a little bit. So it turns out notice it says all children who were admitted to an emergency room in the US in 2012. That's a population. It's over 100,000 kids in this study. So the response variable here is actually, what was the sport that sent them to the emergency room, right? Because we're only measuring one thing in this particular study, right? All of these kids went to an emergency room. It's a population of kids for like one whole year in the US. And you're looking at ones that are already in the emergency room. So the response variable is there a difference in the counts of which sport sent them there? This question could be phrased differently, and often is, and you'll see some problems like this on the homework. You just got to think about this stuff. We could use concussions as the response variable and measure this study differently, but that's not what this particular study shows. This particular study, concussions is part of the sample, right, or the population. So the response variable is what was the sport. So be very, very cautious when you're doing a problem. You have to think about what the response variable is and what the explanatory variable is. Here, there's no explanatory variable. It's only response variable because there's only one variable here. But later on, you might see problems where there's multiple variables, where it might compare concussions between two different sports. And you'd have to look at concussion or didn't get a concussion versus two different sports. For example, if you compare bicycles to football, on this chart, bicycles are responsible for more of the concussions in this year. But overall, if you looked at everybody that rides a bicycle versus everybody that plays football, a lot more kids ride bikes compared to playing football. So bicycles are actually much safer compared to football, just because more than twice as many children ride bicycles compared to football, right? Virtually everybody has ridden a bike, and only about half the people you talk to played football, or less. So you can't, just be careful to not switch the response variable. That's all I'm saying with this. Went a little long, but you understand what I'm saying. And these problems, when you're doing these homework problems, you'll benefit from taking the extra couple minutes to think about it compared to just guessing and getting it wrong because you won't know why you got it wrong. Let's move on. So notation is incredibly important in this class. Not so much in Chapter 2, but once we hit Chapter 3, you will have to have your notation already learned. We're going to introduce almost all of the notation you'll need in Chapter 3 during Chapter 2. So our sample proportion is denoted with that symbol, and it's called p hat. So the rest of the semester, if you see that little guy, you're going to call him p hat. And p hat is computed using data collected from the sample. So it's called the sample proportion, or sometimes you can call it a proportion from a sample. If your proportion comes from a population, then we use the symbol P as noted at the bottom there. And in general, sort of in research, P is generally unknown unless researchers have access to an entire population. So if we just jump back in the notes real quick here, you can see that we've already done a P hat and a P. So let's jump back and look here. These proportions here are all P hats because for rock, paper, scissors, this was a sample of people playing rock, paper, scissors. It wasn't everyone in every tournament. It was just one particular instance of this game. When we did the concussions, this was a population. So if we wanted to write these proportions, all of these proportions would be labeled with a P. So you have to know sample or population before you even know what symbol to write down. Very important. And that's why we started this class with samples, populations, and explanatory and response variables. So sample, population, explanatory, response, all very important. So it doesn't look like we're using that stuff, but we are. To construct these charts, we have to know everything about the variables to even put the charts together. So let's do this example. So we might need the calculator, so I have it handy. So summarize each of the following using proper notation. We saw a student survey in Chapter 1, and it turns out that if you saw the whole thing, it includes 43 students who smoke and 319 who don't. Find the proportion of students who smoke. So we're going to do a number divided by another number, right? Oops. So I'm going to make a fraction again. So we have 43 students who smoke, and we want to find the proportion who smoke. So 43 is definitely going in the numerator. What number is going in the denominator? Are we putting 319 in the denominator? We probably need it, so let's put it in there. So do I hit enter here? So look at what it's saying. Find the proportion who smoke. That means the proportion of all students. How many students were there total? Well, there wasn't 319 total, right? There was 319 plus 43, right? So that's 43 over 362. So again, depending on how your calculator works, it might automatically do that as a decimal. If you have it set up like mine, you have to retype it in to get it to appear as a decimal. So the proportion who smoke, I have not specified how many decimals to round to. So in my answer key here, I keep all proportions to 4 decimal places, and I keep all percentages to 2 decimal places, just to be consistent. On the homework, just follow the directions on the homework. If you have to round, round at the end, right? So that's what I did, right? 43 over 43 plus 319, it's 0.1188. Proportion rounded to 4 decimal places, or 11.88%, percentage rounded to 2 decimal places. On an exam, I really don't care how you leave your answer. You can leave it as a fraction unless I tell you to write it as a proportion. On the homework, just follow the directions for each problem. And notice we labeled it p hat, right? So the p hat is because this is a student survey. A student survey is certainly a sample of students, so we use our sample proportion notation. All right, let's look at part B then. In 2011, it was known that 10% of high school seniors in the US were smokers. Well, there's nothing to compute here. I'm given the percentage, right? So there's nothing to type into the calculator. But I have to know the notation. So high school seniors in the US, that's certainly a population, right? When it says high school seniors, it implies all high school seniors. So that's a population. It's a very large group, millions and millions of people. So the notation there would be P equals 10% or 0.10. And so this is a lot of what you have to do in this class, at least early on, is identify population or sample and then attach the correct notation to it. All right, part C. Of all 1,672, let me start that again. Of all 1,672,965 members of the high school class of 2014, who took the SAT test? That's a mouthful. 793,986 were minority students. So, population or sample? If you're not sure, pause the video and think about it. Okay, well, it says the high school class of 2014. That's going to be a population, right? Because it's all, right? In fact, it says all in the problem. So this is going to get the notation P. But here, the SAT test itself has access to the population. They have all the numbers they need. So it's just going to be numerator divided by denominator. It's always little number divided by big number when you're computing proportions, right? And again, make sure you round it properly depending on what the homework is asking for decimal places. Okay, got one more. Make sure you can get these answers if you're not sure, right? But just follow the directions, right? Either type in a stacked fraction or type it in as a division problem, whatever you have to do on your calculator. It's just the way this app works. Your calculator might work differently. All right, and last one. A survey of 1,060 randomly selected U.S. teens, ages 13 to 17, found that 57% of them made at least one friend online. So, sample or population. This is a sample. Therefore, the proportion we type in will be a p hat, and we're given the percentage, 57%. So all we do is just write p hat equals 57%, or divide by 100% and get 0.57. So some of you are thinking that this is very easy, and that's okay. But the point I want to make, and this is very hard to remember because students will start asking about this in a couple weeks. The focus of this class changes once we hit chapter 3. You have to remember that proportions of samples or populations can be computed or they can be given. Here's a population proportion that's computed. Here's a sample proportion that's given. Don't think that just because it's a sample you have to compute something, or just because it's a population you don't have to compute something. Because that's sort of what happens later, but it doesn't always work. Keep an open mind and just understand that whether you compute it or not has nothing to do with whether it comes from a sample or a population. It has to do with the information you're given in the problem based on the problem setup, right? So just make sure you're aware of that. All right, let's keep going. Oh, my head is too big. So association between two categorical variables. Let me move this over a little bit. I don't want to hide too much. So we're going to look at what happens when we have two categorical variables. What we just finished in this section so far was one categorical variable. Now we're going to look at what happens when we have two categorical variables. How do we measure association? So we're just going to start with an example. I think it's a lot easier to see examples with this kind of stuff. Is smoking linked to difficulty in getting pregnant? A 2011 study collected data on 678 women who had gone off birth control with the intention of becoming pregnant. So the explanatory variable is whether or not the woman is a smoker, defined as smoking at least one cigarette per day prior to pregnancy, or attempted pregnancy, right? And the response variable is whether or not the woman became pregnant during the first cycle off birth control. So this is a very interesting study. You can see how the data were collected here. Nice large study, that's a good sample size. So how do we determine if an association exists between smoking and difficulty in getting pregnant? So what we're going to do is we're going to build visualizations. And the first visualization is just organizing the data, right? And we organize the data into what's called a two-way table. So the phrase two-way table just means rows and columns, two ways. That's all it means. There's no such thing as a three-way table, okay? It's either just a frequency table or it's called a two-way table. And what this means is that we can look at the data two different ways, right? We can look at it as who's pregnant and who's not, and who's a smoker and who's not. So both variables are represented. So notice that the categories for the variable pregnancy status, right? So the variable is pregnant or not, so we're just going to call it pregnancy status. These are the rows. And the categories for smoker status, smoker or non-smoker, those are the columns. Each cell of the table contains the count of the number of data cases that are in both the row and the column categories. So you can see pretty clearly what's going on here. 38 of the women were smokers and got pregnant. 206 were non-smokers and got pregnant. 97 were smokers, did not get pregnant. 337 were non-smokers and did not get pregnant. Everything else that's on this table is just part of the totals. So these are called marginal totals over here because they're in the margins. So 38 plus 206 is 244. So that's all it is. You just add across to get your row totals, or you add down to get your column totals. So we want to answer some questions and look for an association here. So what is the proportion of women successfully getting pregnant after the first cycle? So look at what it's saying here, and we have to use proper notation as well, right? So don't forget. So proportion of women successfully getting pregnant after the first cycle. So we know that we're going to need something in the pregnant row. Just as proportion of women. Notice that the other variable is not mentioned. Smoking status is not mentioned. Therefore, we ignore the smoking status and we just go over here to the row total. So 244 were pregnant out of 678. So that's actually what we type in, right? So 244 divided by 678. So make sure you can get these numbers. I'm rounding to 2 decimal places here just to save space. And there is a homework problem like this, and I think you round to 2 decimal places. So about 36% overall in the entire study, about 36% of the women who tried to get pregnant successfully did within 1 cycle of going off birth control. And notice that I use p hat, right? Because we're talking about the entire sample here. In aggregate, you sum everything up, right? Whenever the total number of people in the study is your denominator, then you just use p hat. Now, what happens when we look at part B here? What proportion of smokers were successful? Well, now we know we're in the smoker column. Successfully pregnant, so we know the numerator is 38. Right? We know our numerator is 38. And here you use the marginal total, 135. Oop, mistake. Still getting used to this ab. Because we need to know, among smokers, how many were successful. So the way this works is that the first word you see, or the word that comes after of, in math, the word of means denominator, okay? So when we say what proportion of smokers, that means the total number of smokers is going in the denominator. Anything after that phrase that goes in the denominator, because it could be a longer idea, here it's just smokers, whatever's left over is your numerator, right? So you'll see proportion, right, or percentage, and then you'll see of. Whatever comes right after of, take that idea and put it in the denominator. So it's 38 divided by 135, right? So it ends up being, 0.28, so 28%. And what proportion of non-smokers were successful? Well, you just use the same exact idea. It's going to be 206 divided by 543. And you're going to get 0.38. So before we move on, because there's plenty more to do in this problem, let's just look at what we have so far. Notice the notation changed. Whenever you have 2 categorical variables and you're looking just at one column or another, or just at one row or another, you have to label your p hats, and you label them according to the category. So here, the explanatory variable is smoker or non-smoker. So that means we're going to have a p hat with smoker attached to it, and a p hat with non-smoker attached to it. So proportion of smokers in the sample who got pregnant was 38 out of 135, or 0.28. So we can kind of see what's going on here, right? So 28% of smokers got pregnant, and 38% of non-smokers got pregnant. This gives us a lot more information than just this, right? And that's actually why they do studies like this. They want to know, is there something about smokers that makes it more difficult to become pregnant? So just looking at the data, just looking at the sample, I would say it does look like these two numbers are not very close together, right? If you're trying to get pregnant, so ladies out there, if you're trying to get pregnant someday, or have, think to yourself, would you rather have a 38% chance or a 28% chance? You'd much rather have a 38% chance if that's something you want to do. And that's actually what is asked on the next slide, right? We're talking about, does there appear to be an association? So compute the difference in proportions, so p hat n minus p hat s, between the groups in parts B and C. So we want to know, what's the actual difference here? And does it appear that there's an association between pregnancy status and smoker status? And then I put a little explain in there because we have to talk about that a little bit. And can we conclude that this association is causal? In other words, can we conclude that smoking is causing the lowered pregnancy rate? Maybe it is, maybe it's not. Let's see. So the difference in proportions, you can go back here and see, we're just going to take, notice it's p hat n minus p hat s, right? So we're just going to go 0.38 minus 0.28, right? We're just subtracting. You'll be told what to subtract when you're doing these problems, okay? Right, so p hat n minus p hat s, 0.38 minus 0.28. And here I rounded to 2 decimal places. So it's 0.1 or 0.10 or 0.10, however you want to put it, it's fine. Because what we do when we subtract proportions is we look at the difference in terms of percentage points. So here, this is no longer a percentage. When you take 38% minus 28%, you don't get 10%. You get 10 percentage points, okay? Because these samples have different sizes, so it's no longer a percent. So we use percentage points. And in fact, that gives us our answer to part E. So does it appear that there's an association between pregnancy status and smoker status? Well, this looks like a big difference to me. If a woman's trying to get pregnant and you're told that, you have this much of a difference, that is indicative that it is a large difference. So that's actually what I said here. Because there's a large difference, 10 percentage points, between the sample proportions, we can conclude that there is a significant association between the variables. So that means smoking status and pregnancy status are related to each other in a non-random way. There's some kind of connection. Does that connection tell us that this is a cause and effect relationship? So if you're not sure, pause the video. If you already printed it out, I know all the answers are given. There's nothing I can do about that. But if you haven't seen the answer yet, think about it. And it turns out this is not cause and effect, or if it is, this study cannot show it, right? Because this is an observational study. This is not a randomized experiment. We cannot assign smoking statuses, especially to women who are trying to get pregnant. So it has to be observational. The researchers can only observe the natural behavior of these women and compute the data. That's it. That's all they can do. So as you can see, there's a lot going on here. And in order to keep the videos in under an hour, that's the only example I'm going to be able to do. So a couple follow-up questions, just follow-up things to think about. When analyzing categorical explanatory variables, we divide the original sample into smaller samples that represent different populations. So in the study we just saw, the different populations were, one population would be all women who smoke who want to get pregnant, and the other one would be all women who don't smoke. But our sample, as we can see, if you go back and look at it, right, the sample isn't huge. So we only had 135 women who smoked and 543 who didn't. And so the idea is that this sample here, this sample of women represents all women, perhaps throughout the United States, who are smokers and trying to get pregnant. And here, these guys would represent all non-smokers who are trying to get pregnant. And the populations represent different categories of the explanatory variable. I just told you about that. And so the response variable is what we measure. So the response variable here is pregnant or not pregnant. So remember, getting pregnant in this study is not the variable. That is a measured value of pregnant or not pregnant, right? All right, so this is how we measure association, is by this thing called a difference in proportions. So the result we came up with is called a difference in proportions of the two samples. So it's a special number that we use a whole bunch in this class, and it is a useful measure of association between two categorical variables. It's not the only measure of association, it's just the only one that we're really going to use, because it's, believe it or not, the least complicated one. If the difference in sample proportions is large, usually around 10 percentage points or more, then this is an indication that an association may be present between the variables in the population as well. So what we saw here with these two samples is that this difference was fairly large. Remember, this has to be a number between -1 and 1. So 0.1 is that's a pretty big difference, right? And so this tells us that maybe this is also true in the population. And that's how statisticians and researchers get stuff done. They take samples, they look at how big this difference is, and that tells them something about the population. So let's look at some visualizations of what we just studied. So first thing we're going to look at is a side-by-side bar chart. And in a side-by-side bar chart, it's similar to the bar charts we just saw earlier, but separate bar charts are given for each group in one of the variables, right? So what we do is we would just, look at the different variables. So there's two variables in this study, they're both categorical, and then we count the response variable categories. So here, this is our smoker, non-smoker, pregnant, non-pregnant. You can see that the bar charts are clustered by the explanatory variable. That's how we generally do it. So just looking at this graph, you can see that the distributions look fairly similar. So just looking at this graph, if I said, do you think that non-smokers would have an easier time getting pregnant? You really can't tell just looking at the graph, right? But again, this shows us all the data. All of the numbers here are the same numbers that were in the table. Let's go back to the table and look at it. See these numbers here? 38, 97, 206, 337. These four numbers, those are the four numbers. Those are these four numbers, right? 38, 97, right? Those are all those numbers. So you're actually seeing the data exactly as it appears in the chart. We also use what's called a segmented bar chart, and this one is not scaled, this first one. Here, all we've done is taken the side-by-side bar chart and stacked all the red parts on top of the blue parts. Look, take the red parts and just pull them up and stack them on their corresponding blue parts. You can just go back and forth a couple times and you can see. So why do we do this? Well, sometimes the information we're trying to get can be more easily seen by segmenting or stacking these bar charts. Again, we can see that the distributions look fairly similar. It doesn't really look like there's a big advantage for non-smoking women trying to get pregnant. But we can scale the segmented bar chart. And what we do is we just take each vertical axis and divide by the denominator, and it scales it all the way up to 100%. Right? So divide by the denominator, multiply by 100%. If that sounds familiar, it should, because that's exactly what we've been computing, these proportions, right? And look here, so the proportion here, 0.38 and 0.28, that's exactly the proportions shown in the graph. So here we can clearly see the difference. Non-smoking women got pregnant at a higher rate. And it's a significantly higher rate. We can see the difference in the two graphs. So the segmented bar chart, the scaled version here, is very, very useful. We can't see the sample sizes anymore, so it does kind of erase some of the information. But if all we care about is comparing those percentages, then this is the graph to go with. So you can see there's lots of ways to display this data, and this is just another way to do it. All right, well, that's it. So here's just a little summary for you, and if you need extra help, you can use the extra practice in the back of the book, or the back of the chapter. And don't forget that there are video solutions for book examples and video tutorials at the end of the section as well in the ebook. So you guys are ready to do the homework, and next video will be section 2.2. So until then, have a good day, and I'll see you next video. Bye-bye now.